So we now begin the next part. We've just completed looking at projectile motion. Now we're going to actually start the process of getting into space. The difference between projectile motion and a rocket, of course, is that we don't throw a rocket into space. We have a controlled explosion which takes it into space. But before we can do that, before we can actually understand how to get to space, we need to understand a few concepts along the way. And the first one that we're going to look at is escape velocity. Okay? Now, this is a very famous lithograph from Newton's understanding of it. Now, we're looking at the blue book on, what page is that? Page 20 there. And I will give you in a few more moments some time to actually complete this section. Before we do that, and before I go through this diagram, we're going to have a look at this. Hopefully it will load by itself.
High hill outside the atmosphere, and through a rock outwards, it would normally be attracted down to the Earth in a parabolic path. But if we threw it at more than 11 kilometres per second, it would escape the Earth's gravity following a hyperbolic path. This velocity is known as the escape velocity. The attraction of gravity deflects the satellite from travelling in a straight path. If the velocity is just right, gravity will keep deflecting the satellite in a circular orbit. The rock is falling in a circular orbit and has become a satellite. If the velocity is a little faster, the orbit will be elliptical. Whatever the shape of the orbit, the satellite will always come back through its launch position.
Okay, now that's just a little quick introduction of what I'm about to talk about. Now, this is called a thought experiment. A thought experiment is an experiment that cannot be performed because of logical problems. And Newton comes up with this idea. He's going to create this imaginary scenario, and from this he is going to deduce that there is existing a certain velocity that you will need to travel through to A, firstly orbit the Earth, and B, secondly to leave the Earth. And this is the way that he imagined it. He said, imagine a very large tower. And here is the large tower. And we're at the top of this tower here. And we're going to be throwing off this tower at a horizontal projection. We're going to be throwing off some cannonballs. And the way we're going to launch it is with the cannon. So here is my first cannonball. It's going to be launched. Off it goes, and down there it hits the ground. Okay? Everyone okay with this? My first launch. We're now going to launch a red cannonball. It's exactly the same as the other one, it's in a different colour. But this time I'm going to use a little bit more gunpowder. And what will happen if I use a little bit more gunpowder? Right, I get a little bit more force, it's going to go further. Okay? And my last ball, my blue ball, we're going to put a lot more gunpowder in. What will happen to the range? It goes even further down there. So the more force that we push, in other words, the faster we push the ball out of the cannon, in other words, the more kinetic energy I give it, the further it is going to land from the bottom of our very, very tall mountain. Now, please realise that the top of this mountain is outside our atmosphere, so there is no air resistance. Because this is a thought experiment, it's not possible to be done. There is no tower on the entire Earth, or mountain on the Earth, which is so tall that it sticks out like a pimple. Okay? And this was his diagram that he drew to try and explain this thought experiment. So here is our Earth, and here is our tower, and here are the three projections that we've just done. Okay, so let's have a look at what has happened. The thing that he suddenly realised, not he didn't suddenly realise, that he realised that the Earth is not flat. It's a sphere. So here are our three balls. The first, the green, the red, and then the blue ball. Okay. They don't just land different distances away from the tower, they also land around parts of the curvature of the Earth. Okay? So are you happy that now we're taking a bit of a step back? This is the shape of the Earth. This is the actual three trajectories that we have just seen. Okay? Are we okay that this is exactly the same as what the last slide was talking about? Right. The thing that we've got to remember is this ball here, the one at the green ball just there, that landed there because we didn't give it as much velocity to start with. It lands further around the Earth over here, the more velocity I give it. Are we okay with that? Right. Excuse my wonkiness in trying to draw that freehand. If I wanted to, if I give this red ball a very large amount of push, it will move from here all the way around, and is it possible to land there? Are we okay that it can land there? How much energy did I need to give that ball? A lot. If I gave it less energy, say for instance, it might have only got around to there before it hit the ground. But keep on giving it more and more energy, it's going to go further and further and further around before it hits the ground. Are we okay with that? So I want you to imagine, once again, the scenario. Let's put this back to where it was. Yep. All the way at the top. Go around. That's it. That's it. Okay. This scenario is the amount of energy I've given this ball is enough for it to go around the Earth and fall at the base of the mountain or tower on the other side. Are we okay with that? Right, yeah. So what have I done to increase the range? Just given a faster push, isn't that right? Okay. So I'm not doing anything special. Here it is. What have I done now? The last trajectory, it fell at the base of the tower. This time, what's it going to do? It's going to strike the tower part way up. Where is it really going to land? Well, in reality, because the tower is still there, it's really gone around once through there. It's supposed to land there, isn't it? But what's it done because the tower's in the road? It's hit the tower halfway up. In reality, it's just simply going not just once around, it's going once and a bit around. Are we okay? So just imagine the tower's in the road and therefore it's bit up the tower. Okay? Next, what's going to happen now? It hits the tower further up. Why is it further up? Right, it's more energy. In reality, it's meant to actually hit around about here again. It's supposed to have gone about once and a bit around, hasn't it? But the reason why it's hitting higher up is because we've given it more energy to start with. What type of energy? Kinetic. And what direction am I projecting this? Horizontal projection, isn't it? Okay. Can you think before I put the next slide up? What is my next slide going to be? Right, it's the one which it goes back to its original position. So, we've just thought, okay, as we give more and more energy to this particle, this cannonball, it's going further and higher up on our mountain. There must be the velocity to which it goes, oops, that's the wrong way, go back, that it goes around and strikes the back of the cannon. Is that clear? So there must be this one velocity that when I project my cannonball, let's put it out there again, out it goes, around it goes. There is this velocity where it will strike the back of the cannon. Now I say to us, what do we know about a horizontal projection? We know something about the horizontal velocity. What is it?
Constant.
Right, ux is constant. Okay? That's a horizontal velocity, the sideways motion. The velocity it leaves the cannon must be the velocity that it re-enters the cannon. So let's think about this. This velocity here now goes around. Does that velocity get any faster or slower? No, it stays the same. And it now comes back to the cannon at the same velocity it left the cannon. I want you to imagine this now. Let's do it one more time. Round it goes. Okay. As before it comes back to its position, it's just stalled there, sorry about that. Before it comes out, we're going to push the cannon out of the road. Okay? Is that what you just said? Yes.
What did you say?
If we pull the cannon out of the road, the ball comes back past us, doesn't it? At the same velocity as it left the cannon. It's as if the cannon relaunches it. Isn't that right? So it will go around there. The cannon's now moved out of the road. It doesn't need another cannon. It just keeps on going and going and going and going. Will it ever stop this? No. Because what do we know about a horizontal projection? The horizontal velocity is constant. At this one exact velocity, it will re-enter the cannon the same speed that it was projected from the cannon. We call this velocity, does anyone know it's got its name? Orbital velocity. Whoops. It's orbital velocity. Right. Now, Newton said, okay, that's orbital velocity. What happens if I now fire it faster than orbital velocity? And he then says, okay, if that's the velocity that will come back to its position, faster than orbital velocity means that it will go off and never return. And so he called this the escape velocity. Now, we're going to escape velocity. We're going to calculate both orbital and escape velocities. There is, however, now he didn't realise this at the time, there is a small difference between orbital velocity and escape velocity through which, if you're at orbital velocity, you'll constantly do a circular orbit. If you are at escape velocity, you'll leave the Earth never to return. But there is a difference between these velocities that if you are travelling at these velocities, you are no longer at a circular velocity, but an elliptical velocity, elliptical orbit. And your orbit becomes so elliptical that eventually, as you get towards escape velocity, it becomes hyperbolic. So there is a difference to say there is velocity, we'll say it's 7, and escape velocity is 11. So you need 7 to go around the Earth, but you need 11 to leave the Earth. At 8, you are no longer in a circular orbit, you become an elliptical orbit. And it becomes more and more elliptical as you approach 11. Are we okay with this? And at 11, you leave and you don't come back. These values are actually quite good because it's actually 7,000 metres per second for the Earth and 11,000 metres per second for the Earth for escape. Okay, have we got any questions on how this worked between Einstein's, but Newton's thought experiment? Okay, right. So, what is escape velocity? And this is on that on the blue book there. That's not the book. What is the definition of escape velocity? Escape velocity is the velocity the launch vehicle must achieve to overcome the gravitational force of the Earth, the gravitational field of the Earth, its pull, and so never return. To achieve escape velocity, we must do work. Now, we know that the way to get work into an object is to change its kinetic energy. And we were doing work on that cannonball a few moments ago by projecting it out of a cannon. So we need to somehow give an object enough kinetic energy, enough work, so that it will never ever return. The amount of work required is equal to the amount of work needed to remove it from the surface of the Earth all the way to an infinite distance away. Where have we heard this definition before? Right, it's the definition of EP. Okay? So here we have a mass on the Earth's surface, and we want to move it from here up to here. Okay? So we're going to calculate that amount of energy that is needed there. Anyone got any questions on what escape velocity is? Escape velocity is the velocity from the kinetic energy that we need to supply to an object so that it overcomes the gravitational pull of the Earth. In other words, we need to be able to move it from here to infinity and never for it to return. Right, okay, to do this, to work out the actual formula, and this is the second part there, which is question 2. Remember, we haven't got anything for question 1 yet. You'll get to do that in a few more moments. We're going to derive the formula for escape velocity. And this has been asked a few times now. So we're going to do this by equating kinetic energy and gravitational potential energy. So to understand why we are doing it, let's work out the amount of energy needed. Just say we're on the surface of the planet, the Earth, it can be any planet, but we'll go there. What is the EP needed? Well, the EP is, down here, is equal to minus g m on r, where m is the mass of the Earth or the planet, and the other m is the mass of the object that we're trying to remove. Okay, the craft, so that's the mass of the craft that we want to escape with. Are we okay with that? The next question I ask is, we need to move it to an infinite distance away. What is the EP at an infinite distance away by definition? It's 0, isn't it? Do you remember that in our definition? So the amount of work needed would be our final EP minus our initial EP. So what's our final EP? What's its value? 0. Okay. Minus the initial EP, which is negative g m on r. And we know that the capital M in that sentence there represents the mass of the planet, and m is the object's mass that we are trying to escape with. Okay, and r is the radius of the planet. Are we okay with that? The two negatives now take care of each other, so the amount of work needed is g m on r. Are we okay with that? So the first question there, or the first part of that question 2 says, by equating this and that, we firstly need to work out how much energy is needed and how to take care of this double negative problem. Okay, are we okay with the amount of energy needed? Where does that energy come from? What do we do with our cannon? Right, we exploded it and therefore it comes from kinetic energy, isn't it? So this is the amount of energy needed. Oops. Joules needed. And we know that it needs to come from kinetic energy. And that there is the formula for kinetic energy, a half mv squared. let's be careful about the little m's and the big m's. What is the little m? Right, it's the mass of the object that we want to escape with. So it's the mass of the craft that we need to achieve escape velocity with. So it's the mass of the moving object. So is this m here and that m here the same m? Yes, that's the mass, because the capital M here is the mass of the Earth. This is an orbit planet that we're on. So what the m appears, little m appears on both sides. So what can I do with it? I can cancel it. Okay. What would v be? V is the velocity we need to project this object at, so that it would meet the amount of joules needed, mustn't it? So let's now make v the subject of the sentence. So we now say that v squared would equal, multiplied with 2 up, 2gm on little r. What is r? The mass of the, the radius of the planet we're starting on. Or the distance from the centre that we're starting from. That's v squared. So what do I get to v? Square root. And it's square root of 2gm on r. And that is the formula for escape velocity. Okay. So we have equated kinetic energy with the work required. And the work required is determined from gravitational potential energy. And from this equating, I've got a formula for escape velocity. How's that? Good. Okay. So we have a simple formula. So what is the only two things that really we need to work with to work out escape velocity? What is the dependence of v upon? Well, let's have a look at what, there are 4 parts of the formula. The 2 and the g are constant, aren't they? So that will never change, because g stays at 6.67 by 10 to the minus 11 no matter where you are in this universe. The first thing it must be dependent upon is the square root of m, the mass of the planet. So v, the escape velocity, is proportional to the square of the mass of the planet. Sorry, the square root of the mass of the planet. Looking on the denominator, there, that the escape velocity is 1 over the square root of the radius. Now, it's hard to work with square roots, but you realise that if I've got a more massive planet, if the mass of my planet goes up, what will happen to my escape velocity? It will also go up. Okay? If the mass of my planet goes down, what will happen to my escape velocity? It will also go down. Okay? So if I go to Jupiter, which has a massive, I can't say a massive mass, it's a larger mass compared to the Earth, therefore I expect the escape velocity on Jupiter to be much greater than the Earth's. Looking over here at the next one, the inverse proportionality. An inverse proportionality says as one goes down, the other one goes up. So if I was to increase my r, as the radius increases, what will happen to my escape velocity? It would go down. Can we see that the reason why we get an inverse proportionality is this is a numerator and that's a denominator. And when you get a relationship like that, when one goes up, the other one goes down. So if I was to decrease the radius of my planet, what should happen to my escape velocity? It will also increase. Okay? Okay. Everyone okay with that? Any questions on that stuff at all? Okay. On page 20, we're just going to do quickly question 4a there, using our formula. 4a says, complete the following escape velocities. We have a mass of our planet, has 5.5 by 10 to the 24 kilograms. The radius of my planet, R, is 6500,000 metres. Please realise this value must be in what? It must be in metres. It's often given to you in kilometres. Just in comparison to the Earth, is this the mass smaller or bigger than the mass of the Earth? Does you remember? It's smaller. Remember, Earth is 5.98 by 10 to the 24. Is this radius bigger or smaller than the Earth? Okay, we just got to get these. It's a little bit larger. The Earth is 6,400 kilometres on average. So just keep that in mind. So we're going to, this is roughly the same size as the Earth. This is a comparable Earth. Okay, so let's work out my escape velocity, V escape, would equal the square root of 2gm on r, which is 2 times 6.67 by 10 to the minus 11 times the mass, which is 5.5 by 10 to the power 24, all over the radius, which is 6500,000. Once that is square rooted, what do I get as my answer? 10,624 metres per second. You often put this into kilometres per second, so that's 10.6 kilometres per second. Okay? The Earth is around about 11 kilometres per second. And the reason why is that the mass is not substantially, but larger. I mean, the mass has more effect on this in this case. Are we okay with how that works? Okay.